friends, today I wanted to do this class equation from my problem point of view. Actually, for that we will prepare a little bit, and slowly we will use some example and to show how to use these concepts in the examples. Okay, these are the concepts very important in the exams, so many times it appears in the exam, especially what are the possible class equation for order 10. This appears in CSIR, NBHM in many exams. We will see a little bit results, little bit about results, then using that we can see what we can do uh, with problems, how to attack the problem using the results. Okay, let's do first thing. I am in finite group setup, so I'll always assume that G is finite group. Okay, so the class equation says that G equal to 1 plus 1 plus dot 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 up to 1 plus C xy x1 and dot 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 plus C xn. The number of ones, it's like another way to write this is nothing but order of center plus summation I equal to 1 to k c n c xn. Okay, this is the number of ones stands for the cardinality of G. That is going to be a very important thing in our way, and this is very going to be a very important thing because it's going to eliminate many possibilities. We can write anything. Okay, so this Cx is nothing but conjugacy class. That means x G inverse. I'm sure you must have seen this from your BSc or MSc, where x belongs to G. Okay, so this is called conjugacy class, and the order of the conjugacy class is there. Okay, the first thing we wanted to observe, the first one, Lagrange's theorem is so basic to us though, so I'm going to use. So suppose G is subgroup, and see, let us, we are in the finite setup, so R of device R of C. This is Lagrange's theorem. It's very important to us, so this I'm going to use this again and again in later without mentioning further. Okay, so first thing we have to observe, the order of center is nothing but number of ones appeared in the class equation. Okay, the second thing we have to observe that each CXI should divide the group order. So I'm planning to do group actions lectures, and after some time, there you can see why this theoretically true, why this kind of results are coming once if I do group action lessons. Okay, and third thing to observe, center of G is always there in set of G. What is this set of G? Okay, what is this set of G is nothing but first center of G is set of all G belongs to G such that Gx equal to xg for every x G. That means I'm collecting only those elements from the group which commutes with every element. Okay, whereas z of x, this x comes from G. I'm fixing x, fixed x. This is nothing but set of all G belongs to G such that Gx equal to xg. See here, I'm collecting only G that commutes with x, whereas here I'm taking all G with commutes, only some G which commutes with everything. So from that it's clear this is true. Why? Because here a element is there, that means it will commute with every other element in the group itself also. So that's why it's going to commute any x. So this is true for This is true for every x belongs to G. So this is going to be a crucial point. And the fourth point is very important. Center of G equal to center of G. I wanted to say that x belongs to center of G if and only if z of x equal to entire G. This is true because if an element belongs to center of G, it will commute with all other elements, right? So an element belongs to center of G, it will commute with all other elements. So here I am taking only G such that Gx equal to xg, but this element belongs to the center, so it will commute with every other element, so that is equal to whole G. Now in the reverse case, if this is equal to whole G, that means this x commute with every other element, that implies x belongs to center of G. See, these four facts are going to be play a very vital role. So again recall, the number of ones appear there is counts the order of G, and each conjugacy class order should divide the order of G. Then always the center inside the any centralizer, this is called centralizer. And finally x belongs to center of G if and only if the centralizer of x is whole G. Okay, how to calculate the centralizer? See, suppose we know the class equation, then this each cxi, right, each cxi, that is nothing but G by z of xi. In the sense, z of xi is the cardinality is nothing but order of G divided by cxi. So this is the idea, and this is how we calculate. And let's do the problem. First problem is a very famous problem. It's appeared in many places. Which are the possible things? Which are not possible? Not possible. I'm going to give like order 10. Order 10 can be written as 1 plus 1 plus 1 plus 2 plus 5, and order 10 can be written as 1 2 plus 3 plus 4, 1 plus 2 plus 2 plus 5, 1 plus 1 plus 2 plus 2 plus 2 plus 2. Okay, from here we will conclude one by one. First of all, look at this. There are three things. Okay, so from here we can conclude center of G order 3, but Lagrange's theorem says that center is also subgroup, so it divides the 10, right? Here order of G is 10, so it divides subgroup, so that is not possible. 3 does not divide 10, so this is not possible. Whereas here, let's see, first center of G is 1, so we cannot do anything because that is 1 divides 10. The second thing is that here look at 3. So I said each conjugacy class separately should divide the order of G, so 3 does not divide 10 again, so this is also not true. But whereas this is true, we can check with D2 into 5. Okay, you will check, just check. Okay, people who have comfortability in algebra, they know. Check with this group. Okay, fine. So why this is not true? I'm going to give more stress on why that is not true. Okay, let us do this case. This is we have to do a little bit carefully. Okay, here everything seems to be okay. What is center of G? Center of G is 2. Each conjugacy class order 2, so 2 divides 10 perfectly, no issue. But still I'm claiming this is not true. Why? So we didn't use other two facts, right? Okay, let's do it the fact. Let us take this element for a moment. Suppose let x belongs to G such that conjugacy class of 2. That implies z of x equal to order of G divided by Cx, that is 10 by 2 equal to 5. Okay, look at that. We already calculated this is equal to 2, right? Now we calculated z of x equal to 5, but we know the third condition says that this is less, I mean the subgroup of here, that means 2 divides 5, which is not possible. So which is not possible, that's why this is not true. Whereas the third option you can check. This is how you eliminate one by one. Okay, let's do more problem. Let us do with reverse way. Reverse way in the sense you will check with the group of order 6. Okay, the group of order 6, if which is possible, 1 plus 1 plus 1 plus 1 plus 1, this is possible. And remember that whenever you get all ones, that is abelian. All ones, because the conjugacy class, remember that gx g inverse such that g belongs to g, when it's abelian, suppose abelian, this will commute. So x alone will be in the conjugacy class. Okay, x will be minimum there, but x alone will be there, so it's 1. In other sense also, if it is everything is 1, it's abelian. Okay, in the order 6, everything is 1 is abelian. Okay, it's only interesting after non-abelian groups. Okay, non-abelian groups, let us do non-abelian groups. Okay, and see, look at that 6 minimum, there should be only at least one, because this is for identity of the group which we are talking about. So the next time it can appear, the devices must be appear, right? Like 1 can appear again, 2 can appear, maybe 3 can appear. We will do case by case. Case center of G equal to 1. Let's do this case. Okay, center of G equal to 1. In the sense 6 is there, I will say 1 plus, now there should be, if 2 appears, suppose I cannot put another 2, because if I put another 2, I have to put, so like totally 5, I have to put 1, so that means center will be higher, so I cannot put another 2, so this is not possible. So 6 equal to 1 plus 2. If a 2 appeared, then I have to put 3 only, then it's okay, it seems to be okay. Okay, and we can check, this is nothing but d2 into 3 or isomorphic to s3. This class equation is for that. Okay, and now this is a case. So suppose 6 equal to 1 plus 3, if I put 3 instead of 2, again I cannot put 3 because it will be like 7. Now I have to put 2, so again this is the same class equation as above, so it's fine. Now let us do the next thing. The center of G equal to 2. Okay, equal to 2. But in the case, what happens? G by center of G. What is the order of G by center of G? It's like 6 by 2 equal to 3. We know every prime order group is cyclic, so G by center of G is cyclic. That implies G is in fact, if and only if G is abelian. This many people knows, right? So it is not possible. In the sense G is abelian means z of G equal to G. So this is not possible. Similarly, center of G is 3 also implies G is abelian. This is a kind of redundant condition. This is not making sense. Okay. So similarly, z of G is 6. That is abelian, of course. So the only possible way for 6 is 1 plus 1 plus 1 plus 1 plus 1 plus 1, and 6 equal to 1 plus 2 plus 3, and these are the only possible, which says is one is abelian, another one is non-abelian. Okay,